Okay, so this will be our last discussion for the midterm period in the lecture component of analytical chemistry. So this is about the electrolyte effect, the thing that we discussed last time. And today we're going to look at how to apply the concept of electrolyte effects in our calculations for equilibrium problems. Okay. So before we go to the application, let us recall that in the presence of diverse ions, the equilibrium is affected. Okay, so the equilibrium may be shifted to the right or to the left. Okay, because of the ionic strengths. Okay, so the reason for that is when we add diverse ions in our solution, what happens is that these diverse ions dissolve into the ionic atmospheres of our, um, let's say, precipitates in that example for that case. Now, so suppose you have a precipitate ion, these diverse ions dissolve into the ionic atmosphere of those precipitate ions, which prevents them from coming back together. And as a result, the equilibrium is shifted to the right. That means the precipitate will be more soluble. So last time we provided concepts about this, and we knew that ionic strengths play a big role when it comes to electrolyte effects. So that means the greater the amount of your diverse ions, the more affected your equilibrium expression will be. Okay. So we also introduced you to the concept of ionic activities and ionic activity coefficient. So usually we write the expression for the equilibrium constant in terms of concentration. But in order to account for the effect of diverse ions, instead of expressing concentrations, we instead use the activities of our ions. And activity of the ion can be calculated when we multiply the concentration of our ion times its gamma or the activity coefficient. The activity coefficient includes the effect of diverse ions, and that can be calculated using the Debye-Uckel equation or the Debye-Uckel limiting law. Okay. However, for our convenience, we already had a table that shows us the corresponding gamma values for each ionic strengths listed there. You can also do linear interpolation if your ionic strengths are within the range but not listed on the columns. Okay. So let's say your ionic strength is somewhere here in between 0.001 and 0.005. Then you can use linear interpolation to calculate for the correct gamma value. Okay. However, if your ionic strength value is greater than the range of this table, so that means, for example, 0.15, 0.2 and above, or 0.001 or below, then you have to use the Debye-Uckel equation or the Debye-Uckel limiting law. Okay, so with that, let's apply all these concepts in calculating for the equilibrium problems involving this concept. Okay, so let's have the first one. So the first question asks us about the molar solubility of silver iodide, whose KSP is 8.3 times 10 raised to negative 17 in water. And then later on, let's check the effect of 0.05 molar potassium nitrate to this uh, to this precipitate. Okay, so to solve for the molar solubility, that can be obtained by solving for the x value of our K expression. Okay, so what's the K expression for silver iodide? So let us show first the dissociation of this precipitate into ions. Silver iodide is a precipitate. It dissociates into Ag plus and iodide ions. Okay. So if we construct the ice table, we will get Ksp equal to the concentration of Ag plus times the concentration of I minus. Using ice table, the concentration of Ag plus is x, iodide is X also. So we have Ksp equals X times another X. Okay. And then to solve for the molar solubility, we just solve for the value of X. That will just be the square root of Ksp. Okay. So the molar solubility of silver iodide in water alone is 9.11 times 10 raised to negative 9 molar. Okay. So that's the molar solubility of silver iodide in water. So as you can see, silver iodide dissolves in a very, very small extent only. Okay. How about in 0.05 molar potassium nitrate? Okay. So what is a potassium nitrate? So potassium nitrate doesn't have any ions similar to our precipitate. So that means this is governed by diverse ion effect. Okay. Because if we have ions from our salt that is the same as silver iodide, then that's common ion effect. Okay. However, our potassium nitrate ions will not produce any ions similar to silver iodide. So this is governed by diverse ion effect. Okay. So that means we have to modify our KSP expression. So we express it last time. We expressed it earlier as the concentration of the two ions. However, this time because we have diverse ions, we have to include the activity coefficients of these ions. Okay. Using ice table, we know that at equilibrium, the concentration of silver and iodide is X. So we have X here and then another X here, gamma Ag plus and gamma I minus. So to solve for the value of X, that is just the square root of Ksp divided by gamma Ag plus times gamma of iodide ions. Okay. So I want you to solve for this, okay, on your own. However, this is the correct equation to solve for the molar solubility, including gamma. Okay. So we already know the Ksp. How about gamma? So for us to identify the gamma value, we should know first the ionic strength of our solution. Okay. So if we have 0.05 molar concentration of 1-to-1 ratio of our salt, okay, so that means this salt will produce one cation and one anion. Okay, their charges are also 1-to-1 in ratio. Potassium is +1, nitrate is -1. So if that's the case, ionic strength is equal to the concentration alone. Okay, so ionic strength will be equal to 0.05 molar already. Okay, that is true when our concentration is 1-to-1 in ratio. Okay. So at ionic strength equal to 0.05, let's look for the gamma values of Ag plus and iodide ions. So let's use the table that we had earlier. So at 0.05 molar ionic strength, the gamma for silver, okay, so this is silver, the gamma is 0.80. And then for iodide ion, that is 0.805. Okay. So for silver, that's 0.80. And then for iodide ions, that's 0.805. Okay. So since we already know gamma, KSP has been given already to us. We can now solve for the X value. It will be the square root of 8.3 times 10 raised to -17 divided by 0.8 times 0.805. And we get the molar solubility of our precipitate in potassium nitrate solution would be that would be 1.14 times 10 raised to -8 molar. So let's compare the molar solubility of our precipitate in diverse ion solution and in water alone. So you can see in water, the solubility is 9 times 10 raised to -9. But for diverse ion solution, the solubility is 1.14 times 10 raised to negative x. So uh, this is a clear evidence that diverse ions do really increase the solubility of our salts, okay, when added to a solution. Okay, so yeah. Okay, so for the last one, let's answer this. Let's calculate the hydronium ion concentration of in a 0.12 molar acetic acid solution. Ka is equal to 1.8 times 10 raised to negative 5 in pure water. Okay, so again, it emphasized that we are in pure water alone. So that means there are no electrolyte effects. Okay. So to solve for the concentration of H3O plus, that can be done with the typical equilibrium equation. All right, so let's show that. And let's show first the dissociation of our acid, acetic acid, into ions. Okay. So acetic acid, okay. So okay. So acetic acid is aqueous. It will react with water to form hydronium ion, H2O or H plus. And it will also form the conjugate base, which is acetate ion. So let's write the K expression for this one. This is Ka because we are pertaining to acid. That will be the concentration of the H3O plus times the conjugate base divided by the concentration of our acid. Okay. Using ice table, okay. Using ice table, we will get Ka equals x times x. And for the denominator, that will be 0.12 minus x. Okay. So in my laboratory class, I taught them the small x approximation. So this problem actually qualifies to a small x approximation technique. So if you want to learn about the small x approximation technique, please look for videos in the laboratory whose title is MTY 1103 sections 2, 6, or 15, um, chapter 4, part 2. Okay. So those are the video titles that explains the small x approximation. Okay, so this problem qualifies to that. Okay, so that will prevent me from using quadratic equation. So this qualifies, okay, to small x approximation. So that means I can simplify this equation as x squared divided by 0.12. Okay. So to solve for x, that will just be the square root of the concentration of acid times the Ka. So I call it the square root of Chaka. Okay. So my laboratory students know that. Okay. So hopefully you also know this. Okay. So the concentration of H3O plus at equilibrium for this acid is the square root of 0.12 times the Ka, and that's equal to 1.47 times 10 raised to negative 3. So that is the concentration of the acid, 1.47 times 10 raised to negative 3 molar in water alone. Okay. However, for the next problem, we still have the same acid, but our solution has diverse ions. So we added 0.05 molar NaCl to our solution. Okay. So earlier we have water, but now we added 0.05 molar of the salt. Okay. What will be the effect? Okay. So NaCl doesn't have any ions related to our equilibrium equation. So again, let's recall the equilibrium equation is given as this. Okay, so this is the equilibrium equation. Sodium and chloride ions are not related to our equilibrium equation. That means this problem involves the use of diverse ion concept. Okay. So instead of writing the Ka in terms of the concentration, we write the Ka in terms of activities, that is concentration including the activity coefficient. Okay. So from this Ka value, we're going to write this with the gamma, okay, with the activity coefficients. Okay, so that will be H plus or H3O. Those two are the same. It's H3COOH. I'm sorry, conjugate base pala. That will be CH3COO minus divided by the acid, CH3COOH. And then we have to include the gamma, gamma H plus, gamma CH3, COO minus divided by gamma of CH3, COOH. Okay. So again, in the presence of the diverse ions, you have to include the gamma, or just simply express your equilibrium in activities. Okay. So using ice table, we can still get the same expression. However, we just added the gammas. Okay, so we have X and then we have another X. This will be gamma H plus, gamma CH3, COO minus, divided by 0.12 minus X times the gamma of CH3, COOH. Okay. So the last problem qualified in the small x approximation. So that means this problem also qualifies for the same. Okay. Okay. So this problem qualifies for the small x approximation. That means I can just simply erase the negative x term here. So I will call it small x. So I can just simply erase that to simplify my equation. So that will be x times gamma H plus gamma CH3 COO minus divided by 0.12 times gamma CH3 COOH. To solve for x, okay, so let's do mental math here. Okay, so to solve for x, that's the square root of 0.12 times the Ka times the gamma of CH3 COOH divided by gamma H plus times gamma CH3 COO minus. Okay, so what I did is that I just rearranged this term to solve for the value of x. Okay, so we have to know first the values of gamma. Okay, so in order for us to solve for the values of gamma, let's look at the ionic strength. The ionic strength is 0.05. Okay, so again, if the salt is 1 to 1 in charge, whatever its concentration is, that whatever the concentration of the salt is, that corresponds to your ionic strength. Okay, so that means mu is 0.05. So now we can look for the gamma of CH3COOH, gamma H plus, and gamma CH3COO minus. The gamma for CH3COOH, or acetic acid, is 1. Why? I told you last time that for uncharged species, gamma is unity. So that means since acetic acid, CH3COOH, is uncharged species, that means its gamma value is unity or equal to 1. Okay? But for charged species such as H plus and acetate ion, we have to look for their gamma values in the table we had earlier. Okay, so let's look at the table that we had uh, and solve for gamma. Okay, so we're still going to use the same column. So this is 0.05 molar. That's our ionic strength. So for H plus or H3O, that's 0.86. And for acetate ion, so please look carefully here. Acetate ion is this. Okay, so that is acetate ion, CH3CO2 minus. Okay, what just happened is that they combine the oxygens. So that's its O2. Okay, So that's acetate ion. The gamma value for acetate ion at 0.05 molar ionic strength is 0.82. Okay. So let's plug it here. 0.86 for H plus, 0.82 for acetate ion. So let's plug all of those in our X. So we will get 12, 0.12 times the Ka. The Ka has been given already. So you're just going to plug it. The gamma of acetic acid, CH3COOH, is 1. For H plus, that's 0.86. COOH minus, that's 0.82. So X is equal to the concentration of H3O plus. Okay, that is equal to the square root of 0.12 times the Ka times 1 divided by 0.86 times 0.82. So we will get X value equal to 1.75 times 10 raised to negative 3 molar. So that is the new H plus concentration in the presence of diverse ions. So let's compare that with the one that doesn't have any diverse ions. So what happened? What happened here is that the concentration of H plus increased. Okay, so from 1.47, we now have 1.75. So let's look at the corresponding pH values. So what will be the pH value for this one? For the acetic acid in water. That's negative log 1.47 times 10 raised to negative 3. The pH is 2.83. Okay, so that is the pH in this solution if it is in water. However, if you add salt, what happens? It becomes more acidic. Okay, so let's solve for the pH. That's negative log 1.75 times 10 raised to negative 3. So the pH is now 2.76. The pH became lower. So we have 2.83. Now we have 2.76. Again, when we have lower pH, that means it is more acidic. Okay. So actually, I do this whenever I am making some condiments. Okay. So especially when my dinner or let's say lunch is, let's say galunggong. Okay. So any fish will do. So when I want vinegar as my condiment, I add salt in the vinegar. Okay, what happens when I add salt in the vinegar? So as you can see, we just we just shown here in our calculations that when we add salt in our vinegar solution, so CH3COOH is just the vinegar. Okay, so when we add salt to our vinegar, the pH decreases. So that means it becomes more acidic. Okay, so I'm a fan of very acidic vinegar solutions. So uh, I really love when my vinegar is maasim. So when it is very sour, especially when my food is, let's say, tapsilog or fish. So that's the reason why I add salt in vinegar to apply the concept of electrolyte effects. Because we just proved here in our calculations that addition of salt makes the pH of this acid lower. So that enhances the flavor. Okay. So that's one of the practical applications of this concept. Okay. So I hope by this time, if you want to make your vinegars more sour, okay, so if you want to make it more sour, then you add salt. Okay. So that will enhance the flavor, and with that will end. That is all for our discussion today. Before I end this recording, I just want to go through some announcement. So let's look at your Canvas. So in your Canvas account, I already posted worksheets about Chapter 4. So look at the announcements, additional resource material. I already uploaded a worksheet for Chapter 4. So I want you to practice on this. on these two items with some few uh, items below it. Okay, and then here's the activity coefficient table. So please take a screenshot or save this in your phone. And then here's the calculation for all of all of those stuff. Okay, so I showed here the calculation. Okay, so yun. Okay, so I hope that this will help you with your review. Okay, if you want to look for laboratory worksheets, I also have some here. Okay, however, I'm still going to update it once the chapter 4 worksheet is available. Also, other than the worksheets, I will open a quiz for this chapter. So I will open a quiz for this chapter maybe around Wednesday until Saturday. Okay. So for this chapter, that will be your last quiz for this chapter. Also, I made a mock midterm exam for the laboratory and the lecture. Everyone can join. Okay, so suppose I'm your lecture instructor. If you want to take my mock exam for the laboratory, you can also do that. These two are ungraded, okay, because this is just mock exam. So this is just for you to test if you can ace the midterm exam. Okay, so this is composed of around 25 questions. Only one attempt will be given because for the midterms, one attempt will be given to you. Okay, and this is good for 45 minutes because this problem, I mean, this test only has 25 questions. So kaya yun na yun. Okay, so again, taking these two exams, these mock exams are optional. You may take it, you may not, but I hope you do because this will help you to assess whether you're prepared for the midterm examination next week. Okay, so again, I will open quiz for chapter 4 by Wednesday until Saturday, and then the mock exams will be open starting Saturday until Sunday, the day before the midterm. Okay. So yeah, hopefully all these materials will help you assess if you understood the topics. Okay, and I hope that you will use my resource materials here for when reviewing. Okay, so that will be all for the midterms. Maybe I'll see you again by next week for the grade consultation. Okay, so stay safe as always, and also don't forget, if you want to make your vinegar more sour, just add salt. Okay, that is governed by electrolyte effects. Okay, so that's my technique why I enjoy eating food with vinegar. Okay, so hopefully you do the same. Okay, so that will be all, and I'll see you again next time. Stay safe.